Hello, my name is Jean-Baptiste Tristan, and I am presenting the paper A Formal Proof of PAC Learnability for Decision Stumps. This is work that was done in collaboration with Joseph Tesserotti from Boston College, Kundinya Vacha from the University of Pittsburgh, and Anindya Banerjee from IMDEA. When we think about a compiler, if we're trying to answer the question, what's a good compiler? Of course, we might want that the compiler generate efficient code. We might also want to make sure that the compiler preserve the semantics of the program being compiled. The question that motivated our work was, what kind of properties can we prove about a machine learning algorithm? Of course, there are very important properties that we could prove about a machine learning algorithm or a machine learning classifier. For example, we might want to prove that the classifier respects some privacy properties, some fairness properties, or some robustness properties. But the question we're asking here is, are there more fundamental properties about what we might want to prove about the process of learning? To answer this question, I will need to explain a little bit of learning theory, and to that end, describe a very standard model for supervised learning. To model the problem of supervised learning, we can start by saying that there is a domain, X, and there is a function, a labeling function that we often call the target, and that is here denoted by tau, that associates 0 or 1 to every element in a domain. We also have a distribution mu on the domain X, and we do not know what tau is, and we do not know what the distribution is. In the learning problem, we choose a hypothesis space that is a subset of all of the functions from the domain X to 0, 1. And we're going to collect a training set. The training set is a set of pairs, xi, tau of xi, where the first element xi is simply taken from the domain by actually sampling from the distribution of a domain, and tau of xi is the result of labeling our data point with function tau. A learning algorithm takes as an input the hypothesis space and a training set, and is going to return one hypothesis from the hypothesis space, the chosen hypothesis. Once this training phase is done, we can use our chosen hypothesis H to classify new data points. So given a data point X from the domain, we can use our hypothesis in X to decide some value Y, 0 or 1. We can define what is the error of a classifier. If you consider any of the functions H in our hypothesis space, then we can consider the following event, the subset of the domain for which our hypothesis classifies a data point differently than tau, the target function, the labeling function. This event captures the idea that the classification is incorrect. By considering the distribution over the domain, we can define the classification error of a hypothesis H as the probability of the event that we just described. Probability which is measured by the distribution mu over the domain. So the error of h is the probability that the classification is incorrect. One of the fundamental problems in trying to apply machine learning is the bias variance trade-off. And the key question is, why does my classifier have a large error? Two possibilities might be that the hypothesis space is too small. If the hypothesis space is too small, it might not contain tau, in which case it's impossible to have enough data points to mimic perfectly the labeling function tau. It might even be so bad that the functions in the hypothesis space are all actually behaving very differently from tau. This is the problem of underfitting or bias. We could also have the problem that the hypothesis space is too large. And if it's too large, it might actually require a lot of training examples to do a good job for the learning algorithm at choosing a hypothesis. This is the problem of overfitting or variance. So ideally, if we're trying to answer the question, what is a good classifier? How can we ensure that the learning process gave us a classifier that has some qualities in terms of error, of generalization error, right? We would like to say something about the relationship between the hypothesis space, how big, how complex the hypothesis space is, and the size of our training set. That is the data set that we've been given, or is it size of the data set that we've been given, a good match for the complexity of our hypothesis space? That can help us make sure that we have enough data given the hypothesis space that we're choosing. That can also allow us to make sure that we're unlikely to end up with a misleading data set. The theory that can allow us to formalize these ideas and prove something about the learning process is PAC learnability. Here's the formal definition of PAC learnability. We're going to say that a hypothesis space is probably approximately correctly learnable, or PAC learnable, if, in a sense, we can prove that there is an algorithm that, regardless of what is the accuracy that you would like to establish, and what is the confidence that you would like to establish, we can collect a data set that is big enough to provide these guarantees of accuracy and confidence. More formally, we require the existence of a so-called sample complexity function that, for a given accuracy and confidence, will tell us how big the training set needs to be. And we require the existence of some algorithm A, such that for any accuracy epsilon that we might want to achieve, for any confidence delta that we might want to achieve, and regardless of what tau, the target function, and mu, the distribution over the domain, are, we can construct a data set S where all of the x are sampled from the distribution mu. The labels are the image by tau of xi, and such that the size of S, the number of examples in S, is greater or equal to the sample complexity for the desired accuracy and confidence. Then, with probability at least 1 minus delta, the error of the hypothesis chosen by the algorithm, the learning algorithm, on the training set S is less or equal than epsilon. So what this is requiring is that for a fraction 1 minus delta of all of the possible data sets that we could sample, data sets of size at least m of epsilon and delta, the error of the resulting hypothesis will be less than epsilon. In this paper, what we do is to develop a formal proof of PAC learnability for a specific class, the hypothesis class of decision stumps. And we do so in the Lean Proof Assistant. As part of this, we ask the question, what is the ratio of algorithmic reasoning to the math annoyance? What I mean by this is, how much of the effort for the formal verification of such a PAC learnability property correspond to the type of reasoning that we might find in a textbook, as opposed to having to establish a lot of results of measurability of functions, etc. And then the second question is, how can we organize such a development? Can we isolate the parts of the development that have to do with reasoning about the algorithm, as opposed to establishing all of the required property from measure theory and so on? The problem of decision stump is very simple, but it's the classic example in learning theory, to introduce learning theory, because it really characterizes what a proof of PAC learnability should be. So in this case, the domain is the real line, and the labeling function is simply a value on the real line, tau, such that any point on the real line that is less or equal to tau is labeled here as a blue circle, and any point on the real line that is greater than tau is labeled as a red cross. We're here making the assumption that the data is linearly separable, and that all of the blue circles are on one side of tau, all of the red crosses are on the other side of tau. In this simple problem, we can consider the following hypothesis space. So in general, this should be a function. It's going to be the function that associates to a given point its label, but we can actually identify it here for simplicity simply with points on the real line. So if we're given a training set, a set of examples, the ones that we see here on this example, and now that we're actually considering specifically the set of all of the points of R to be a so-called decision stump to help us decide whether a point should be labeled as a blue circle or as a red cross, we can develop our algorithm. The algorithm is going to be very simple. We're going to return the rightmost blue point from our training set. There are other choices that could be made, but this one is simple enough. And now the question is it the case that if I choose any accuracy epsilon and any confidence delta, I can make sure that I will have a training set that's big enough so that I can pick a value on the real line that will guarantee that with probability 1 minus delta, the error of the point I have chosen will be less than epsilon. A standard intuitive proof goes like this, to prove that this algorithm in fact has this property. Now, if we're trying to achieve some accuracy epsilon, let's consider the region of the real line that goes from some point A all the way to tau, and which has probability the measure epsilon. Now, the question is, what is the probability that we're going to have a classification error? Well, in this algorithm, we pick the rightmost blue point. So if we had a point that actually fell in that region, then we would have to actually choose that point and the region would actually be smaller. So the probability of an error is actually simply the probability that all of our n training examples, all of our n samples to construct the training data set, actually missed the region from A to tau. because if one had been in that region, then we would actually have an accuracy of less than epsilon. And the probability of missing this region n times is simply 1 minus epsilon power n. Now, all we need to do to establish PAC learnability is to make sure that we can actually choose n such that 1 minus epsilon power n is less than delta, which is any confidence that we want to choose. And in fact, this is doable. This example and this proof is what you will find in all of the classic learning theory books, typically in the first or in the second chapter. Now, these proofs are written to give an intuition about what PAC learnability is and how to prove it. Interestingly, this proof that I just sketched, which you can find in these books, is not completely precise. And here's a counterexample. You could say that tau is 0.5, that mu is a Bernoulli distribution parameterized by 0.5, which means that half of the mass will be on 0 and half of the mass will be on 1. And now if you try to achieve an accuracy of 0.25, you have the problem that for every possible A, the probability that A will fall in that region is 0.5 is if A is less than or equal to 0 and 0 otherwise. Which means that you cannot actually consider a region A to tau of probability exactly 0.25. And the problem is not with PAC learnability, the problem is with this proof that I sketched before, and the error that I made when I sketched the proof was to just assume that we have a region of mass exactly epsilon, which might not be the case if we have a point mass just at the wrong place. Now, interestingly, by using the proof assistant, we can prove that decision stumps are PAC learnable in very much the same way that we would do in a textbook, without being encumbered by these technical details, and all the while making sure that all of the proof is precise. And in fact, making sure that we avoid this counterexample in the proof is what turned out to be the most difficult. So let me just give a very high-level description of what the proof looks like and how we structured it. The algorithm implementation is very simple. The algorithm itself, the learning algorithm, is deterministic, right? Because all we do is choose the rightmost point. But its input is a random sample. And so to formalize our learning algorithm in a lean proof assistant, we simply used the jury monad. Another part of the proof is to formalize all of the properties of the algorithm, which in a sense simply boil down to making sure that we are in fact returning the rightmost blue point. So very simple. We also have to prove some mathematics results. For example, we have to prove that the algorithm is a measurable function and therefore that any piece of code involved in the training algorithm is a measurable function. We also need to prove that the events we're interested in are a measurable set. And of course, as we do the proof, we end up with all kinds of different events for which we need to prove measurability. And finally, we also have proof that have to do with the problem that I raised, the counterexample, where we need to show that we can actually always pick a region of probability measure less or equal to epsilon. And we need to make sure that these points always exist. Now, the final part of the proof, which is what we would expect to actually find in a textbook, is the statement, the probabilistic statement, and the high-level reasoning, where what we have to do essentially is to show that the algorithmic property leads to properties over the the sets or the events, which in turn lead to probabilistic properties. Overall, the implementation of the algorithm is trivial and correspond to 20 lines of code. Proving the properties of the algorithm is also, I think it's fair to say that it's trivial, and it's 150 lines of code, but it's important to know that we really favored readability, and these proofs could have been shorter. Now, proving all of the results that we depend upon, like measurability of functions, measurability of sets, etc., represent about 900 lines of proofs. And interestingly, some of these proofs are conceptually difficult. To be clear, they would not be conceptually difficult to a mathematician. I think these are proofs that a college student might have to prove in a measure theory class or in a class on real analysis. But compared to the type of reasoning that we have to do to prove the properties of the algorithms, they are much more difficult. Finally, the probabilistic statement and the high-level reasoning, which correspond roughly to what we actually write in the textbook, to what you actually find in the textbook, correspond to about 500 lines of development, and is fairly routine and easy probabilistic reasoning. As I mentioned, aside from trying to evaluate how much difficulty comes from all of the results in measurability, etc., what we're interested in is trying to better organize the development to, if possible, separate the algorithmic reasoning from the fundamental results in measurability. This is what we did, and in fact, we were able to do this very cleanly. We have, on the one hand, the definition of the algorithm and the proof of its basic properties. And isolated from this, we have all of the proofs about measurability and analytic results that we depend upon. Building on these, we can prove the part that is about the probabilistic reasoning. This part obviously depends heavily on the algorithm definition and the properties of the algorithm. But very nicely, with just a tiny amount of automation to make sure that the proper premises are discharged, we can actually develop all the probabilistic reasoning without having to worry about the results on measurability and analytic results. That is that in the end, we have a development where the proof actually correspond to a good level to a textbook proof, and the dirty details about measurability, etc., have been hidden in this module that the proof depends upon. All the details can be found in the paper. You can also look at the documented proof that you can find on the wiki on GitHub, where you can actually see the development, where every different piece has been, we tried to make sure to put them in different files and making sure that the development was as clean as possible and that different parts were isolated from each other's. And all of this is documented. And finally, I think it's important to mention that overall, working with Lean was a very positive experience. And 3 out of the 4 authors were familiar with the Coq Proof Assistant, but had no familiarity with the Lean Proof Assistant. But to a large extent, we were able to just pick up Lean and start working with it. And really what makes Lean shine is the MathLib library, which contained all of the results that we needed in measure theory, also for the analytic result, some results in basic topology, etc. And that actually made the reasoning not only doable but very pleasant. And that's it. Thank you very much.